Assalamualaikum and a very good day to all. So we are going to discuss topic 7, which is electromotive force and circuit. Okay, the things that you need to understand here is what does it mean by electromotive force and how to calculate for the resistor in series and parallel. And the last one going to be, we are going to use one concept or one method which is we call as a Kirchhoff, where this method is basically used to solve complex circuit and for you to find more than one unknown. Okay, so let's start. Okay, so for us to understand how the currents flow inside the circuit, definitely we need to understand the source of the electromotive force. Okay, so for us to maintain a steady current inside the circuit, definitely we need to have an EMF. Okay, so EMF can be any device that going to change from chemical or mechanical or light into electrical energy. Okay, so basically these devices are going to provide a potential energy of the chargers where this EMF also provide a potential difference for charge to move. Okay, so the easiest device that you can actually see is going to be a battery. So battery are going to provide a possible voltage or possible potential difference. So what happened is the charge are going to move, therefore the current are going to pass through the circuit. Okay, however, okay, this source of EMF doesn't give us a real voltage to the circuit. Okay, example, if we have 5 volt of the battery, doesn't mean that the 5 volt are going to provide inside the circuit. It can be like 4.98 volt, it can be 4.84 volt. Okay, the reason why is because the existence of internal resistance. The internal resistance happen inside the battery. So charge are freely to move between the electrodes. However, it's not going to like smoothly move because there are some hindrance inside the electrolyte. So what happened is this is going to be the one that provide the internal resistance to the battery. Okay. So the things that you need to understand here is we are going to denote our EMF as this kind of symbol. Okay, so without internal resistance, what happened is your EMF going to be equal to your terminal voltage. Okay, the things that you need to understand is the terminal voltage is an actual voltage. Okay, so like I mentioned before, if we have like 5 volt of battery, doesn't mean that going to provide you 5 volt. It can be less, it can be more, based on concept of charging or discharging. Okay, so that one we call as the actual voltage, which this actual voltage are the one that going to control the amount of current inside the circuit. Okay, so if you have EMF that basically if you have internal resistance inside the battery, so your terminal voltage can be more or can be less than the EMF. This one depends on charging and discharging concept. Okay, so mostly we are going to use this equation for us to find the terminal voltage, or we can actually say that as the actual voltage. So the VT is basically a terminal voltage, so it means that for you to find the actual voltage, it means that you need to EMF minus with the IR. Okay, but this one is the concept of discharging. Okay, so we are going to discuss discharging and charging after this. Okay, the things that you need to understand that doesn't mean that only EMF source have an internal resistance. It can be any electronic equipment. It can be ammeter, it can be voltmeter. So this one you need to incorporate your internal resistance inside your calculations. For example, if you have like ideal voltmeter or ideal ammeter, okay, it means that this electronic equipment doesn't have internal resistance, therefore your EMF going to be equal to the terminal voltage. Okay, so let's now discuss about discharging and charging concept. Okay, so when it comes to the discharging, is basically any kind of chemical energy, any kind of mechanical energy, and that energy going to be converted into electrical energy. Okay, so it means that you are going to withdraw some current from the potential difference. Okay, and is going to turn on the light or the easiest way, the easiest application that you can actually see it when you use the handphone. Okay, so when you use the handphone, you can actually see that the battery of your handphone are going to be reduced with the increased amount of usage of the handphone. Okay, so that one we call as a discharging. Okay, so how do we get that formula? Okay, the things that you need to understand here is, okay, doesn't care whether it's external or internal resistance, there'll always be a voltage drop. Okay, there'll always be a voltage drop because the resistance are going to be the one that provides some obstacle for the charge to move. Okay, so example, if I have like resistor and I connect it with the battery, and the current basically moving from positive to negative. Okay, so positive to negative, which means that it's going to be in this direction. Okay, so this is going to be the EMF. So here going to be the voltage drop at the internal resistance. Okay, the things that you need to understand here is the terminal voltage is the only concept where you need to find the voltage at the battery or at any power supply device. Okay, so when the current flow from positive to negative, or you can actually see that from here, from the negative to the positive terminal, the EMF that you are going to get is going to be a positive value because it's moving from lower potential difference to the higher potential difference between the terminal. Okay, and that's the reason why you are going to get the EMF. Okay, and then it's going to become a minus here. The reason is because of there'll always be a voltage drop at the internal resistance or any kind of resistor. Okay, so that's why you are going to get here is IR, because IR is basically a voltage drop at the internal resistance. Therefore you are going to get actual voltage, that these voltage are going to be the one that provide a potential difference inside the circuit. Okay, the terminal voltage. Okay, so the things that you understand here is the EMF is the one that we call as the original voltage without any current flow. So example, if you see the label at the battery 5 volt, that one going to be EMF, which means that it doesn't connect to the circuit yet. Okay, but once you connect to the circuit and there's an internal resistance, then that one we call as the terminal voltage. Okay, okay, so let's now discuss about the charging concept. Okay, when you charge your handphone, that one we call as a charging concept. Okay, means that the battery are going to be filled with the 100% of the energy. Okay, so the charging concept is the reverse from the discharging, where you are going to convert electrical energy to chemical energy. Example, like your handphone, when you charge your handphone. Okay, okay, so like I mentioned before, there's always be a voltage drop at the internal resistor or external resistor. Okay, and this one going to be connected to the battery. Okay, so example, if the current flow from negative terminal to the positive terminal inside the circuit, which means that it's going to move from positive terminal to the negative terminal, then your EMF here going to be negative value, because it's moving from higher potential difference to lower potential difference, and that's the reason why you are going to get negative in front of this equation. Okay, and then because there's always be a voltage drop, okay, at the resistor, that's why you are going to get minus IR, which means that you are going to get minus terminal voltage. Okay, but to make it easier for you to calculate, you can just cancel out all the minus. Therefore, for the charging concept, the equation going to be the original voltage, okay, plus with the voltage at the internal resistor. So this one we call as a charging concept, and you can see that the value of terminal voltage is more than the EMF of the battery. Okay, so this is one of the questions where we can actually practice our understanding about the EMF, about the internal resistance. Okay, so let's start. Okay, so basically what happened is you are going to have a 65 ohms resistor that going to be connected to the terminal of the battery, whose EMF is 12 volt and whose internal resistance is 0.5 ohm. Okay, calculate the current in the circuit. Okay, 65 ohms resistor is basically external resistor. Okay, the things that you need to understand here, the internal resistance always be less than 1 ohm. Okay, but internal resistance can be increased because of the age of the power supply. Therefore the electrode is going to be dry, therefore the internal resistance is going to be increased. Okay, so internal resistance is basically around 0.05 ohm, 0.1 ohm, which is very very small, but can be increased because of the age of the power supply. Okay, so the 65 ohms here is the external resistor. I'm going to denote it as per capital R. Okay, and the internal resistance here is going to be 0.5 ohm. Okay, calculate the current in the circuit. Okay, so if example the question doesn't give me any picture, okay, so you can actually assume that the circuit is discharging. Okay, if the question want to state charging, is going to provide you with a picture where the current flow from negative to positive, that one going to be a charging, or the question need to state about charging terms. Okay, therefore we're going to use different kind of equations for the charging concept. Okay, but this one, as you can see that from the picture itself, the current moving from positive to negative, so definitely this one going to be discharging. Okay, so the moment you see this charging concept, definitely your equation is going to be terminal voltage equals to EMF minus IR. Okay, the terminal voltage here, okay, because the current already flow, which the current is the actual current, therefore this current are going to flow inside the external resistor. Therefore I'm going to put it as the IR. Okay, EMF minus IR. So rearrange the equations. So you are going to get here is IR plus IR equals to EMF. Factorize the I, R plus R. Therefore you are going to get this equation for you to find the current. Okay, so DMF is going to be 12.0, so the external is going to be 65 plus with the 0.5 of the internal resistance. Therefore you are going to get the answer is 0.13 ampere. Okay, next question asks you about the terminal voltage of the battery. Okay, so you can actually use this equation for you to find the terminal voltage, which is VT equals to 12.0 minus with the internal voltage, which is internal resistance or voltage drop at the internal resistance, so 0.183. The internal is going to be 0.5, so you are going to get your terminal voltage, or we can actually say that as the actual voltage, which is 11.9 volt. Okay. So for question C, the question asks you to find the power dissipated in the resistor. So power dissipated can be called as heat. Okay, so heat is basically one of the power dissipated, and that's an example. If the question asks you about only power dissipated, therefore you need to focus on the resistor. Okay, so here we are going to use the formula where we are going to relate with the resistor. So it's going to be P equals to I square R. So P equals to I square R, therefore current is going to be 0.183 square multiplied by the resistor, which is 65. Okay, so you are going to get your answer is 2.18 watt. This one going to be power dissipated at external resistor. Then you use the same formula for you to find the power dissipated for the internal resistor. Okay, 0.183 square, internal resistance is 0.5, so you are going to get here is 0.02 watt. Okay, which is basically less than the power dissipated for the external resistor. Okay, this one going to be a little bit different from the previous question that we already solved. Okay, this one, the question asks you to find the EMF and the internal resistance of the battery. So basically what happened here is when you connect with the resistor, which is external resistor of 4.5 ohm, the current that going to be withdrawn from the potential difference is going to be 0.3 ampere. Okay, but when you change that resistor into 9.5 ohm, the current going to be 0.15 ampere. Okay, so we are going to use the concept of discharging circuit. Okay, so we are going to use the formula of terminal voltage equals to EMF minus IR, but this one I'm going to put as a I capital R, EMF minus IR. Okay, so I here going to be 0.3 multiplied by 4.5. So we didn't know about the EMF. also for the internal resistance. Okay, so put it just R here. So here you are going to get 1.35 equals to EMF minus 0.3 R. So it's going to be the first equation. So we are going to find the second equations, where you're going to have 0.15 multiplied by 9.5 equals to EMF minus 0.15 R. So you are going to get here is 1.425 equals to EMF minus 0.15 R. Okay, so this is going to be the second equations. Okay, so we are going to solve this using simultaneous concept. Okay, so I'm going to put it 1.35 equals to EMF minus 0.3 R. Okay, so using the simultaneous part, so I'm going to get here is 0.075 equals to 0.15 R. Therefore, you are going to get your internal resistance, which is 0.5 ohm. Okay, so once you get the internal resistance, definitely you are going to get the EMF. Okay, so I'm going to put the internal resistance where I get here into my first equations, where so I'm going to have 1.35 EMF minus 0.3, 0.5. So the EMF that I'm going to get is going to be 1.5 volt. Okay, now we are going to discuss the arrangement of resistor, whether it's going to be in series or parallel. Okay, so we are going to start with the series first. Okay, when we talk about a resistor in series, it means that we are going to connect it like one long wire, but this one we connected with using resistor. Okay, so what happens is we have R1, R2, and R3. Okay, example, if we talk about current, definitely we talk about electron flow. So electrons are going to flow from negative to the positive terminal. Okay, so it's going to be in this direction. Okay, so what happens is electron only have one path for it to move, and that's the reason why the current in R3 will be equal to the R2, and it will be equal to the R1. Okay, so the current equivalent, which is the total current, will be equal to the I1, I2, and also I3. Okay, and how about potential difference? Okay, so this one is a positive, which means that we are going to connect this side with the positive one. Okay, and this one is a negative, so we are going to connect this one with the negative terminal of the battery. Therefore, as if the combination of voltage at R1 will be equal to the voltage at R2 and the voltage of R3, which this combination will be equal to the EMF of the battery. Okay, so you can actually state here as a V equivalent, which is the EMF of the battery, will be equal to the V1 plus V2 plus V3. Or you can actually say that once the electron here move through the R3, is going to lose some energy. Okay, energy of the potential energy, which is going to be U equals to QV. Okay, and then when it pass through R2, it's also lost another energy, which is going to be QV2, and when it's passed through R1, is also lost another energy, which is QV3. So the combination of the total potential energy here will be equivalent to the potential energy provided by the battery. Okay, and then you are going to get the same, which is the potential difference at R3, R1, and R2 will be equivalent to the EMF of the battery. Okay, so from this equation, we can actually derive that based on the Ohm's law, V equals to IR. So here I'm going to put it as a I equivalent, R equivalent equals to I1, R1 plus I2, R2 plus I3, R3. Which means that because of current going to be the same for R1, R2, and R3, therefore we are going to get our formula for the series connection going to be R equivalent equals to R1 plus R2 plus R3. Okay, let's move on with the parallel arrangement. Okay, when we talk about the parallel arrangement, so it means that it's going to be like this. So we put this put as the R1, R2, and the R3. And this resistor going to be directly connected to the potential difference, which you can actually say that this positive side are going to be at this positive one connected with this also positive one, this one also positive one. Same goes as the negative terminal connected to this one, and this one. Therefore, we can actually say that the R1 also have the battery, have the voltage that going to be equivalent with the EMF of the battery. So it means that the voltage for R1, R2, R3 going to be equal to the EMF of the battery. Okay, and how about the current? Okay, so when we talk about the current, definitely we talk about electron flow. So the electron flow are going to be in this direction, and because electron here have like additional path, it can actually pass through R1 or R2 or R3. It means that the electron flow for each resistor going to be different. However, based on our understanding that the current going into will be currents going out, and the concept of conservation of charge, the total charge moving for R1 plus R2 plus R3 will be the combination of the electron flow given by the energy by the battery. Okay, because charge is conserved, therefore the current that flowing into will be equal to the current flowing out. So we can actually state that the current comes from I1 plus with the I2 plus I3 will be equal to the I equivalent or total current. Okay, based on the Ohm's law, V equals to IR, so I going to be V over R. So we are going to put it here as a V1 plus R1 equals to R1, V2 over R2 plus V3 over R3 will be equal to the V equivalent over R equivalent. Okay, because voltage for each resistor will be equal to each other and also equal to the potential difference of the battery. Therefore, our equation for parallel resistor will be 1 over R equivalent equals to 1 over R1 plus 1 over R2 plus 1 over R3. Okay, so you can actually say that, okay, based on our previous chapter where we are going to have the equations of resistor equals to resistivity length over area. So you can actually see that when you increase length, which is basically the arrangement of series, you are going to increase the resistor. Okay, and if you increase the area, which you can see that you increase the surface area or the path for the electron to move, you are going to decrease the resistor. So we can conclude that the understanding of arrangement in series and parallel equal with the previous chapter of concept of resistor. Okay, so this is the summary of what we have learned before, which is the parallel and series of resistor. Okay, so for you to solve the question when it comes to the arrangement or combination of parallel and series, make sure that you start your calculations with something with the physical quantity that same for each resistor. Okay, it's much easier. This one calculation is almost the same like capacitor. Okay, where you are going to find the equal physical quantity first, the same physical quantity first, and after that you are going to find the difference of the physical quantity for each capacitor. So this one also the same thing. You are going to solve using the same physical quantity for each resistor, and after that you are going to find for the one that difference for each resistor. Okay, so we are going to start with the concept test first. Okay, so the light bulb here are going to be identical. So which configuration produce more light? Okay, whether it's going to be series or parallel. So definitely the answer going to be parallel. The reason is because the resistance here going to be less than the resistance here. Okay, because 1 over R equivalent equals to 1 over R1 plus 1 over R2, which is going to produce a small resistance value in compare with this one where you are going to get a large value. Okay, and which way do you think the headlight of the car are wired? So definitely it's going to be parallel. The reason is because of if one of the light bulb is broken, there's still current flow to another light bulb, and that's the reason why the headlights are going to be connected in parallel. But if example you connected in series, example if like one light bulb is turned off or broken, there's no current flow to the next one, okay, because this one we can call it as like open circuit, which means that the current cannot pass through to the next one, okay. Okay, so the headlights of the car are wired in parallel, which is same as the one that inside the building. So means that inside the building the wire are going to be arranged in the parallel in compare with the series, okay. With the same reason, because if example like one part of the arrangement is broken, so still current can actually flow there. But example if you like connected using the series, one part is broken, definitely there will be no current flow, okay. Okay, let's move on with the next one, which is this one is calculation questions, okay. So you have two identical resistors that are connected with 24-volt battery. How much current is drawn from the battery when the resistor is connected? So the first thing that you need to do is you need to find the R equivalent, okay. So if example you arrange that resistor in series, so means that you are going to use the equation of R equivalent equals to R1 plus R2, okay, which means that it's going to be 200 ohm, 100 plus 100, okay. And then you are going to use the concept of V equals to IR for you to find the current flow, which is the voltage is going to be 24 and is going to be 200 of the resistor equivalent here. Therefore you are going to get your answer is 0.12 ampere. And for the parallel, you are going to use 1 over R equivalent, which is going to be R1 over R1 plus 1 over R2. So you're going to put as 1 over 100 plus 1 over 100 here. Okay, so you need to find the R equivalent. Make sure that you don't forget to put 1 over R equivalent, okay, because that is the most common careless mistake that I found in my students, okay. Okay, so you are going to get here is 50 ohms. Use the same formula, which is I equals to V over R. So 24 divided by 50, therefore you are going to get your answer is 0.48 ampere. And we can actually say that the current flow for the series will be less than the current flow for the parallel arrangement of resistor. Okay, so this is the questions where you need to find the resistor equivalent first for you to find the current drawn from the battery. Okay, so make sure that you find the resistor equivalent first. Therefore, please solve resistor that in parallel first. Okay, then combine it, become one, and then you move to the next step, whether it's going to be series or parallel with the next one. Okay, so the 500 and 700 definitely going to be resistor in parallel arrangement. So you are going to find the 1 over R equivalent for the first one, which is going to be 1 over 500 plus 1 over 700. Okay, so find the R equivalent 1 first, which is going to be 291.7 ohm. Once you find the resistor equivalent for this combination, so it becomes 1 here with the value of 291.7. So these 291.7 are going to be in series with the 400 ohm. So you are going to use the formula for series, which is going to be R equivalent 291.7 plus with the 400. Therefore, the R equivalent is going to be 691.7 ohm. Okay, so once you find the R equivalent, then you can actually find the current drawn from the battery. Okay, using the formula for the Ohm's law, which is V equals to IR. Okay, so I going to be V over R. So here you are going to get 12.0 over 691.7. So the current drawn from the battery will be equals to 0.0173 ampere, or you can actually put it as a 17 milliampere. Okay. Okay, so the same question, but the question now asks you to find the current through the 500 ohm and also 700 ohm. Okay, so like the previous one, we already find the current drawn from the battery, which is 0.0173 ampere. Okay, like I mentioned before, for the series part, the current will be the same value. So the arrangement of 500 plus 700, the combination of this is going to have like one resistor, which is going to be equivalent to 291.7 ohm. And this 291.7 ohm in series with the 400 ohm. Therefore, the current flow in through the 291.7 ohm will be equal with the 400 ohm, which will going to be equal with the 0.0173. Okay, so from there, you know that current flow inside 291.7 will be 0.0173 ampere. So from there, we need to find the voltage, okay? Because when it comes to the parallel arrangement, the one that going to have the same value is going to be the potential difference, okay? Okay, using the concept of Ohm's law, so the V going to be equals to IR, so I is 0.0173, and you multiply with the R equivalent of 500 and 700, which is 291.7. Okay, so you are going to get here is 5.06 volt. Okay, so it means that the voltage at 500 and 700 will have the same value, which is 5.06 volt. Then from there, definitely you can actually find the current using the same concept, which is the Ohm's law. So the I at 500 ohms will be 5.06 divided by the 500. So you're going to get 0.010 ampere, or you can actually put as 10 milliampere. And the same thing that you are going to do for the 700 ohm. Okay, 5.06 over 700. Therefore, you are going to get 0.007 ampere, or you can actually state as a 7 milliampere. Okay, so that's how you do it. Okay, so for this one, this is the combination question, which is consists of resistor in series and parallel, but it's going to be arranged in like a diamond shape. Okay, but this one, okay, you can actually solve it using the concept of current is like a flow of water. So example, if there's no junction, then definitely it's going to be a series, but if you have a junction, definitely it's going to be a parallel. Okay, so this one, 25 ohms, 10 ohms, 15 ohms, there's no junction here, therefore this combination going to be in series. Okay, so the combination of 25, 10 and 15 going to provide you with the R equivalent one, going to be 25 power of 3 plus 10 power of 3 plus 15 power of 3, which is going to be 50 kilo ohm. Okay, so this combination going to be 1. Okay, and the combination here are going to be in vertical position. Okay, so this is the combination of 25, 10 and 15. So this is going to be parallel with the 50 kilo ohms. Okay, so you solve this thing first. So you are going to get here is 1 over R equivalent 2, which is going to be 1 over 50 power of 3 plus with the 1 over 50 power of 3. So you are going to get here is 25 kilo ohms. Okay, 25 power of 3 ohms. Okay, so the combination of this, so definitely is going to be like 1 here, okay, which are going to be in series with 35 kilo ohms, and also going to be in series with 40 kilo ohms. Okay, so we are going to solve that. So we're going to get R equivalent 3, which is 25 power of 3 plus with the 35 power of 3 plus with the 40 power of 3. So you are going to get here is 100 kilo ohms. Okay, so like I mentioned before, when you arrange this thing, it's going to be like one combination resistor, and it's going to be arranged in vertical positions. So it's going to be like here. Okay, so this is going to be 100 kilo ohms. Okay, so the 100 kilo ohm here are going to be parallel with the 100 kilo ohms here. So you are going to get that one is 1 over R equivalent 4, which is 1 over 100 kilo ohms plus with the 1 over 100 kilo ohms. So you are going to get here is 50 kilo ohms. Okay, so the combination of 100 kilo ohms and 100 kilo ohm are going to be like one resistor, which we are going to connect it like here. This is going to be 50 kilo ohms. Okay, so 50 kilo ohms are going to be in series with 5 kilo ohm and 5 kilo ohms. Okay, so you are going to get here is R equivalent, which is the total. Okay, so 5 power of 3 plus 5 power of 3 plus with the 50 power of 3. Therefore, the total resistor equivalent for this arrangement is going to be 60 kilo ohm. Okay. So for this kind of question, make sure that you solve it one by one. Okay, because we want to avoid confusing when it comes to the arrangement. Okay. Okay, so make sure that you solve it one by one. Okay, so the same thing that you are going to do for the second one here, but this one, we are going to solve it using concept of alternate, where we are going to start with the series because 10 and 2 here is going to be in series, and it's going to be like parallel with the 6 ohm, and alternate means that series parallel, series parallel, series parallel. Okay, okay, so let's start. Me feel this fire, nothing gonna care love. Heart's gonna catch again. Break your heart, back girl. Mad boy, oh, oh, oh. Let a nigga try for mine and cry for me. You rain fall in love. Coping. Okay, for you to solve this question, make sure that you always start with the opposite side of the battery. So a battery is going to be connected at this side, so it means that you are going to start from this side first. Okay. Okay, so 10 and 2 ohms definitely are going to be in series, so we are going to get one, that one is R equivalent 1 as a 12 ohm. So I'm going to skip some working step here, but I think you already know how to calculate using series and parallel. Okay. Okay, but the combination of 10 and 2 ohms is going to be in the vertical position, where we are going to put it as like this. Okay, so this is going to be the R equivalent of 1, which is going to be parallel with the R9, which is 6 ohm. Okay, so the combination will always be in the vertical position here. Okay, so for you to find the next R equivalent, okay, so we are going to have 1 over 12 plus 1 over 6. You are going to get here is, you're going to get 4 ohms here. So the combination of these three are going to be arranged in the parallel part also. So it's going to be like this. This is the R equivalent 2, which will be in series with the R7. Okay, 8 ohm. Okay, so there's mono here. Okay, so because in series, so for us to find the R equivalent 3, so just add up everything. So 4 plus 8, so you are going to get 12 ohm. Okay, so the combination of here, make sure that always put it in the vertical position. Okay, so it's going to be parallel with the R6, which is 6 ohm here. The combination of here is going to be R equivalent 3 here. So because it's parallel, therefore we are going to use 1 over R equivalent 4, which is going to be 1 over 12 plus 1 over 6. So you are going to get here is 4 ohms. Okay, so you are going to have arrangement that is going to be in series with the 4 ohms. Okay, so this combination going to be like one resistor but in series with the 4 ohms. Okay, so R equivalent 5. Okay, this is the R equivalent 3. So 4 plus 4, then you are going to get 8 ohms. Okay, so the 8 ohms over there are going to be parallel with the 8 ohm. Okay, so here is going to be 8 ohm here, going to be parallel with the R4, which is 8 ohm here. So you are going to get R equivalent 6, going to be 1 over 1 over 8 plus 1 over 8. Therefore, you are going to get 4 ohms. Okay, so the arrangement of that combination, this one with this one, are going to be in series with the 4 ohms at the R3. Okay, so in series, therefore I'm going to put it as here is R equivalent 7. So you are going to get 4 plus 4, which is 8 ohm. Okay, and the 8 ohms of the R equivalent 7 here are going to be parallel with the R2 8 ohm here. Okay, so R2, which is 8 ohm. So you are going to get your answer here is R equivalent 8, which is going to be 1 over 8 plus 1 over 8. You are going to get your R equivalent 8 as a 4 ohms, which is going to be in series with this 6 ohm. Okay, so the total R equivalent here are going to be R equivalent total, which is 4 plus 6. Therefore, this combination have a 10 ohms of R equivalent. Okay, so you can actually see that the arrangement of this going to be series, parallel, series, which is alternate. Okay, so if I going to be conclude this thing to make it simple for you, so the 10 and 10 2 here is going to be series, parallel with the 6 ohm, and the combination of this going to be series with the 8 ohm here, and this combination going to be parallel with the 6 ohm, series with the 4 ohms here, and going to be parallel with the R4 here, and the combination of this going to be series with the 4 ohms and parallel back with the 8 ohm, and finally is going to be series with the 6 ohm. Okay, so this concept we call as the alternate method. Okay, let's move on to the last part, Kirchhoff rules. Okay, so like the previous one, you can solve that questions using a very simple method, which is Ohm's law, because you need to find only one current. But when it comes to the complicated circuit where you are going to find I1, I2, I3, or any physical quantity where you need to find more than one, definitely Kirchhoff rules are the one that are going to help us to find it. Okay, so the Kirchhoff rule can be separated into two laws, which is going to be, one is junction rules, another one going to be loop rules. So another name for the junction rule or loop rule is going to be current law or Kirchhoff voltage law. Okay, so basically the current law is use the concept of conservation of charge. Okay, so it means that the charge cannot be created, cannot be destroyed. So example, if you have like 50 coulomb, definitely after that you also have a 50 coulomb. So this concept relate with the current. So example, if you have like 50 ampere going into the junction, definitely you are going to have 50 ampere, the combination going to be 50 ampere also. Okay, and the voltage law here, we are going to use the concept of conservation of energy. Like conservation of charge, energy cannot be created, cannot be destroyed, can change to other form of energy. So the concept here is the sum of changes of energy or potential difference inside the closed loop always equal to 0. Okay, it cannot be like example at the initial part you have 50 joule, and suddenly at the final part you are going to have 60 joule. It means that it cannot be happen like that, because suddenly you have a additional 10 joule. Okay, that 10 joule additional need to be converted into other types of energy. Okay, because we assume that the energy before and after should be equal. Okay, so let's start with the first rule, which we call as the junction rule, and this junction rule relate with the current. Okay, and it use the concept of conservation of charge. Okay, so example, if you have like junction, okay, this current you have 50 ampere, and then you have a junction here, so it means that the current here going to be I1, and this one I2 and I3. Okay, so if you have 50 ampere going into the junction, definitely the combination of I2 and I3 also have 50 ampere. Okay, so that is the concept of junction rule, where the sum of the current in entering the junction or into the junction will be equal to the sum of the current leaving the junction. Okay, that is for Kirchhoff junction rule, or we can call it as a Kirchhoff current law. Okay, let's move on to the next rule. Okay, so here is a Kirchhoff loop rule, which is going to relate with the concept of voltage or potential difference. Okay, and what happened is the sum of potential difference across all the element, or the changes, or the sum of the changes across the closed loop always equals to 0. So example, if you start with 50 joule at the end you are going to have a 50 joule. Okay, so the changes here are going to be 0, and that's what happened for the Kirchhoff loop rule, where they are going to relate with the concept of conservation of energy. Okay, so how to start using this Kirchhoff rule? Okay, the first thing definitely that you need to do is you need to draw first the assumption loop. Okay, it can be clockwise or anti-clockwise. So you can actually see that from the circuit, okay, you have one space here and you have one space here. So basically it's going to be two space, which means that you need to draw two assumption loop. Okay, so you can actually draw clockwise, or anti-clockwise, or clockwise. So if I draw this one is clockwise and this one going to be anti-clockwise, so I am going to have two assumption loop, which means they are going to have two equation. Okay, so example, if you have three space, it means that you are going to have three assumption loop, therefore you are going to have three equation. Okay, so once you draw the assumption loop, okay, this assumption loop, I need to remind you, it can be different with your friends. Okay, if your friend choose both anti-clockwise and you choose both clockwise, what happens is at the end you are going to get the same answer. Okay, because here the concept of Kirchhoff rule, the assumption is going to be always correct, but the current here, the one they're going to be draw inside the circuit, example, if I draw like this one, this is going to be I1, this is going to be I2, and this is going to be I3. It's going to have a different current because it's a parallel arrangement. The current here may be right and may be wrong. So we are going to prove the answer, whether it's going to be right or wrong based on negative and positive of the final answer. If you get negative answer for your current, it means that the current inside the circuit is wrong. Okay, not your assumption. The current, which is I1 and I2, I3, might be wrong. And if you get positive answer for your current, it means that the direction here, I1, I2, and I3, is going to be correct. Okay, that's how we do it. Okay, so once you draw with the assumption loop, then you need to use the concept of Kirchhoff currents law, which is junction law, relate with the current, and you need to use the Kirchhoff voltage law, relate with the loop. Okay, so these two law, we have four rules for it to use. Okay, two for resistor. Okay, it can be internal, it can be external resistor. For internal resistance of the battery, please assume that as an external resistor, which is going to be easy. Okay, and another two rules going to be for the battery or any power supply or any EMF. Okay, so how to use that rule? Okay, let's start. Okay, so we are going to start with the use of law inside the resistor. Okay, so we are going to compare between the directions of assumption loop, which you already draw, whether it's going to be clockwise or anti-clockwise, and you are going to compare it with the current inside the circuit. I'm going to put the SEC and AL. Okay, this one is going to be assumption loop, and this one is going to be current inside the circuit, which mostly the questions already draw it for you. Okay, so this one can be right, can be wrong, but please take note, your assumption loop always be correct. Okay, so example, this one you are going to look only at the resistor. Okay, if your assumption loop moving in the same direction with your current inside the circuit, then the voltage there going to be negative value. Okay, if your assumption loop in the same direction with your current inside the circuit, the voltage there going to be negative value. It means that you need to multiply V, which is equals to IR. R is going to be the resistor that you are going to focus. Okay, current is going to be at that particular path. So example, if you focus on the resistor that currently at the current I1, so it means that is going to be V equals to I1 times with the resistor that you are going to find the voltage there. Okay, so example second, okay, if your assumption loop opposite with your current inside the circuit, okay, then it means that the voltage at the resistor there going to be positive. Okay, yes, I know that at the resistor there's always be a voltage drop, but this one we use the method, the concept. Okay, the method. So the method state that if we have a same direction, it means that negative value of the voltage drop or voltage there, and you are going to have a positive value if the directions of the currents inside the circuit and the assumption loop in the opposite direction. Okay, these two focus only on the resistor. It can be external, it can be internal resistor. Okay, next one. Okay, this one we are going to focus at the battery or any power supply. Okay, before I start explain how to use the Kirchhoff current law and Kirchhoff voltage law for this one, okay, please make sure that you can actually use the terminal voltage. Okay, example, if you want to use the terminal voltage, it means that you are going to detect first whether it's going to be charging or discharging. Then you need to find the terminal voltage, but it's going to be a little bit tedious for you to do it. Therefore, you just put your internal resistance like external one, like I mentioned before, and then you just use EMF, which is the original voltage, for you to solve using this method. Okay, which is going to be very easy. Okay, so for this one, okay, we only focus on the potential difference or power supply. So here you are going to focus on assumption loop. Okay, your assumption loop is the one that going to decide the sign of your voltage, whether it's going to be positive or negative. Okay, so example, if your assumption loop is moving from negative terminal to the positive terminal, okay, please look only at the terminal, between the terminal. Please don't look at the circuit. Okay, that one going to be different. Okay, only focus between the terminal. So example, if moving from negative to positive, which is moving from lower to higher potential difference, therefore your EMF going to be positive. Okay, if your assumption loop moving from positive to negative, okay, so it's moving from higher potential difference to lower potential difference between the terminal, therefore your EMF over there, you are going to get negative EMF. Okay, so as you can see that both concept, resistor and potential difference of the battery, are going to use concept of voltage, which is this one. We are going to use concept of Kirchhoff voltage law, or we can call it as a Kirchhoff loop rule. Okay, loop rule. Okay, for you to use the concept of Kirchhoff current law, okay, Kirchhoff current law, or we can call it as a Kirchhoff junction rule. Okay, the things that you need to understand here is the sum of the current entering the junction will be equal to the sum of the current leaving the junction. So example, if you have junction like this, okay, this is like I1 and this is I2 and this is I3. Okay, so if the current entering the junction, you can actually put it as a positive current. Okay, and the current leaving the junction, you can put it as a negative. Okay, you can actually use the vice versa concept, where the current entering the junction is negative, the current leaving the junction is positive, and you are going to get the same answer. Okay, because, okay, example like this one, okay, we need to come up with the equation. Okay, like Kirchhoff voltage law, we need to come up with two equation because you have two assumption loop. This one, you need to come up with one equation, which is altogether you have three equation for you to find the unknown. Okay, so for this one, okay, example, if I state that the current into the junction going to be positive, the current leaving the junction going to be negative, therefore my equation here going to be I1 because it's entering the junction, minus with the I2 because it's leaving the junction, and minus with the I3 leaving the junction, and equals to 0. Okay, and that's the reason why you can actually make it vice versa, which means that entering the junction is negative, leaving the junction is positive, but at the end you are going to get the same answer. Okay, whatever things happen, make sure that it's always equals to 0. Okay, because we want to state that if you have a current of 50 ampere going into, and you are going to have a total of current leaving the junction is 50 ampere, therefore the changes is equal to 0. Okay. Okay, so let's start with this question. Okay, let's practice with this question. Okay, so the question here asks you to find current I1, I2, and I3. The reason you need to find the three current is because this arrangement is parallel. So definitely you have a different value of current. Okay, and after that you need to find the terminal voltage for each battery. Okay, so if the question state terminal voltage, definitely you only focus on the battery, but you need to find the current first before you find the terminal voltage. The reason is because you need to decide whether it's going to be charging or discharging based on the current that you are going to find. Okay, and once you find the terminal voltage, then you need to find the potential difference from A to B. Okay, so let's start. Okay, so the first thing first, when you have this kind of question, definitely you need to draw your assumption loop. Okay, so it's up to you. You can draw clockwise or anti-clockwise, or you can actually use clockwise anti-clockwise. Okay, example, if I use one is clockwise and another one is anti-clockwise. Okay, so you have two space here, means that you are going to have two equation. But before I'm using the Kirchhoff voltage law, I'm going to come up with the equation from the Kirchhoff current law, which I'm going to focus on the I1, I2, and the I3 direction. Okay, so you have two junction here at A and D. You need to choose either one. Okay, if you choose A, just focus on A for you to come up with the Kirchhoff current law. If you choose D, then that one you're going to focus to come up with the Kirchhoff current law equation. Okay, so if example, if I've choose A, okay, so now my I1 going to be leaving the junction, I2 also leaving the junction, so both are going to have negative value. Okay, but I3 here is going to be entering the junction at A, therefore it's going to be positive value. Therefore my equation is going to be negative I1 minus I2 plus I3 equal to 0. Okay, this is going to be my first equation, which is come up for Kirchhoff current law. Okay, so these equations are going to help us to find the unknown. Okay, so next is we are going to come up with the equation for the Kirchhoff voltage law. So here we are going to have two equations, therefore I'm going to solve with the first one. Okay, the first one, my assumption loop is going to be in clockwise motion. Okay, so I'm going to start with the 30 ohms. Okay, so because my assumption loop here is the same direction with the current I1, therefore the 30 ohms going to have negative voltage. So I'm going to put here as negative 30 multiplied with the I1 there. Okay, and there's no more resistor at the path of I1. Okay, therefore we need to focus at the path of I3. Okay, because your equation here are going to consist of this one whole loop. Okay, I'm done with the path of I1. Okay, now I'm going to focus on the path of I3. Okay, so I'm going to start with the 45. Okay, so when it comes to the potential difference, you only look at the terminal and you only focus on the assumption loop. So your assumption loop here is clockwise motion, so it's moving from lower to higher potential difference. Therefore here you are going to have plus 45 because it's moving from lower to higher potential difference. Okay, and then for 1 ohm and 40 ohm, okay, because the current assumption loop there is going to be in the same direction with your current inside the circuit of I3, therefore 1 ohms and 40 ohms are going to have negative value. So here I'm going to put it as a negative 1 multiplied with the I3, and another one is going to be negative 40 I3. Okay, equals to what? Equals to 0. Okay, why is going to equal to 0 is because, like the definitions of the Kirchhoff voltage law, the sum of changes around the closed loop always equals to 0. Okay, so you solve this. Okay, simplify it. Therefore you are going to get here is negative 30 I1 minus 41 I3 equals to negative 45. Okay, so you are going to have first equation. Okay, so now we are going to focus for the second equation. Therefore I'm going to draw the second assumption loop, which is going to be in anti-clockwise motion. Okay, so your second equation also consists of this one whole loop, which means that also consists of path of I3. Okay, because we are going to use the concept of simultaneous, therefore we need to have like one unknown that basically same for equation 1 and equation 2. Okay, so I'm going to start at 20 ohms. Okay, because my assumption loop, going to be like this. Okay, assumption loop here. Okay, my assumption loop going to be in the same direction with my current inside the circuit, which is I2. Therefore, at 20 ohms and 1 ohm here, the voltage there going to be negative value. Okay, same direction, negative, opposite direction going to be positive. Okay, so the second equation going to be negative 20 I2 minus with 1 I2. Okay, and then focus at the potential difference of the battery here. Okay, because your assumption loop, okay, we are going to use assumption loop, not current inside the circuit for our potential difference at the battery. Okay, is moving from where? It's moving from lower to higher. Therefore, your potential difference here, 80 volt here, going to get positive value. Okay, so it means that here lower to higher potential difference, therefore 80. Okay, and then done with the path of I2. Okay, double check everything, make sure that you include all the resistor there. Okay, then you focus on the path of I3, because like I mentioned before, this one whole circuit going to be included in your equation of number 2. Okay, so we focus on the path of I3, okay, and focus on the loop, second loop. Okay, so it's moving from, okay, for the potential difference is going to move from lower to higher, okay, based on our second loop here. Therefore, our equation here are going to become lower to higher, so it's going to be positive 45. Okay, moving from higher potential, lower potential to higher potential. Okay, and then we focus at the resistor 1 ohm and 40 ohms. Okay, we are going to look at the current inside the circuit and assumption loop number 2. Okay, because it's in the same direction, therefore is going to be negative voltage at 1 ohms and 40 ohms. So here I'm going to put it as a negative I3, 1 times I3, and minus with 40 I3 equals to 0. Okay, simplify everything. Therefore, you are going to get your equation is negative 21 I2 minus with the 41 I3 equals to negative 125. So this is going to be your second equation. Okay, the things that you need to understand, you are going to use your calculator to solve the simultaneous part. But for you to use that calculator, you need to make sure that the unknown is same for equation 1 and equation 2. Okay, so now we have I1, I3, and this one we have I2 and I3. Both need to have the same unknown. Okay, so I'm going to change maybe this one, which means that I'm going to make this equation with the unknown of I1 and I3. Okay, please make sure that you didn't change the same unknown. Okay, if you change this thing, it's going to be a lot of work. You are going to repeat the same thing. Okay, you change the unknown that not the same from both equation, like I1 or I2, so you can choose I1 or I2. Okay, but now I'm going to choose I2 here, where I'm going to use my Kirchhoff currents law here. Okay, so Kirchhoff currents law, I'm going to put my I2 as subject, which is I2 equals to I3 minus I1. Okay, so I3 minus I1 here, I'm going to insert that into this equation. Okay, so I'm going to get here is negative 21 I3 plus 21 I1 minus 41 I3 equals to negative 125. Simplify everything, therefore you are going to get your equation is 21 I1 minus 62 I3 equals to negative 125. So this is going to be my the third equation. So this one here I'm going to put inside the calculator together with this one here. Okay, because you already mix the unknown there to be the same value, which is I1 and I3. Here the unknowns also I1 and I3. Then you can actually put it inside your calculator. Okay, I already put the equation 3 and number 1 to my calculator. Therefore, I'm going to get my I1 is going to be negative 0.8 0.86 ampere. Okay. Okay, once you get the negative value here, means that the current inside the circuit, the direction is wrong. Okay, so it means that you need to give a statement here, because your current I1 here is moving clockwise motion. Therefore, you need to put the correct direction, which is the current I1 should be anti-clockwise direction, to make sure that the current into the junction will be equal to the current leaving the junction. Okay, if you have I1 which is in that direction, it means that it's going to disobey the concept of Kirchhoff current law. Okay. Okay. So we also got I3, which is my I3 going to be 1.73 ampere. Okay, if I get positive here, it means that the directions of I3 here, which is correct. Okay, so it means that with this direction, the currents going into the junction will be equals to the current leaving the junction. Okay, so now we already have I1 and I3, therefore we can actually find I2, okay, using this equation. Okay, so I'm using this equation for me to find the I2. So I'm going to put it as I2 equals to I3 is 1.73, and the I1 is negative. You need to put the negative there, okay, because these equations we solve using the wrong current direction. Therefore, we need to use the wrong current direction to find another unknown. Okay, so negative 0.86. Therefore, I'm going to get my answer is 1.73 plus 0.86. Therefore, I'm going to get my answer is 2.59 ampere. Okay, so you already find I1, I2, and I3. Once you find this three current, therefore you can actually proceed to the next question. Okay, so the next question is you need to find the terminal voltage for each battery. So you can actually see that the terminal voltage for each battery here is 45 volt and also 80 volt. Okay. Okay, but the things that you need to understand here is before you find the terminal voltage, you need to look at your answer at A, because if you get negative current, you need to fix that thing first before you use the charging or discharging formula. Okay, so here the I1, I get negative here. Okay, but there's no battery there. Okay, my I3 and my I2, I get both is positive. It means that the direction is correct. Okay, once I fully confirm the direction is correct, or I already fixed to the correct direction, okay, therefore I'm going to see whether it's going to be charging or discharging. Okay, for the EMF2 here, because the current moving from lower to higher potential difference, okay, or if you feel hard for you to decide whether it's charging or discharging, you can just imagine that this current is moving like this inside the circuit. Okay, so it's moving from higher potential difference to lower potential difference inside the circuit, which means that this one going to be discharging. Okay, discharging. Okay, so I'm going to use the formula of discharging, which is going to be terminal voltage equals to EMF minus IR. Okay, EMF going to be 45 minus current for the I3 is 1.73 ampere. Okay, so 1.73 multiplied with the internal resistance of 1 ohm. Okay, so you are going to get your answer is 43.27 volt. Okay, okay, let's look at the EMF1 here. Okay, so the I2 is moving from lower to higher potential difference between the terminal, or if you feel that it's very hard for you to see that, then you need to imagine for the circuit. It means that it's moving from higher to lower potential difference inside the circuit, which is this one also discharging. Okay, so VT equals to EMF minus IR, which is EMF there going to be 80 minus with the current at I3. Sorry, it should be I2, okay, which is 2.59. Okay, and internal resistance is going to be 1 here. Therefore your answer here, you are going to get 77.41 volt. Okay. Okay, so that's how you solve for the terminal voltage. But the things that you need to understand here, please make sure that you double check your current. If you get negative current there, make sure that you fix that thing first before you decide whether it's charging or discharging battery. Okay. Okay, so this is another additional note. Okay, for you to find the terminal voltage here, you need to use the direction that has been corrected, and then after that you can decide whether it's going to be charging or discharging formula. Okay, another things that you need to know also when it comes to the question asks you about the potential difference, example from A to B, use any path, better to choose two path, but this one you choose path with the correct currents. Okay, means that you already fix the direction, then you can actually proceed to find the potential difference. Okay, I'm encourage students to use two path, because when you use two path and then you get the same answer, it means that your answer for the I1, I2, I3 definitely correct. Okay, so make sure that you choose two path, any path from A to B. Definitely you are going to get the same answer, but the difference is going to be whether you are going to get negative or positive. Okay, but that one doesn't affect your answer so much, because potential difference is scalar, so we only look at the value. Okay, at the magnitude. So like the number C, the question asks you to find the potential difference from A to D. Okay, from A to D. Okay, so basically you can choose path A to D here. Okay, or you can choose path A to D here, or you can choose path A to D here. Whatever path that you choose, you are going to get the same magnitude of potential difference. Okay, so I'm going to choose my first path, going to be in this direction. Okay, the I3 that I get is positive, therefore the direction here is already correct. Okay, so I'm going to draw a big loop. So you assume this like a big loop. Okay, this like a big loop. Okay, okay, so A to D. Okay, so use the concept of Kirchhoff voltage law. Okay, so if your assumption loop here, the blue one is the assumption loop, is the same direction with your current I3, therefore it's going to be negative. But this one, the direction is opposite, therefore 40 ohm, they're going to be positive. So 40, okay, but the I3 here, you already know the value, so you just insert the value of I3, which is 1.73. Okay, and then for 1 ohms, because the assumption loop and the direction of the current inside the circuit is in the opposite direction, therefore you are going to get positive value. So plus with the I3, which is 1.73. Okay, and then for the battery here, you are going to look only at the potential, only at the assumption loop, which is moving from higher to lower potential difference. Therefore here you are going to get is negative 45, which is going to be equals to 25.93 volt. Okay, so for me to prove whether my answer is correct or wrong, it's better for me to choose another path. Okay, so I'm going to choose this path. Okay, but here my I1, I get negative, therefore the direction is not going to be clockwise. The direction here going to be anti-clockwise, like that. Okay, okay, so I'm going to fix that direction. It's going to be anti-clockwise. Okay, so because my assumption loop, which is the green one, okay, I draw it like the one big loop here. Okay, opposite with the fixed direction of current, therefore my 30 ohms, they're going to be positive value. Okay, and there's no more resistor or battery here, therefore the 30 ohms multiply with the answer from I1, which is 0.86, which is going to be equal to 25.8 volt. Okay, you don't have to be worried because the difference is around 0.01% or 0.1%. It doesn't affect so much, but still both answer accepted. Okay, so means that the answer that you get for I1, I2 and I3 is correct. So if you want to check whether your path of I2, you are going to get the same potential difference, you can do that, okay, but still you are going to get the same answer. Okay, so let's try to choose this path, okay, whether we are going to get the same answer or not. Okay, so the I2, the current there is positive, therefore you don't have to fix that. Okay, the direction is already correct. Okay, so here I'm going to like draw one big loop from A to B. So at the battery, my assumption loop is moving from lower to higher potential difference. Therefore, I'm going to put it as a positive 80, okay, minus with the internal resistance. So the voltage here going to be negative because my assumption loop and my current inside the circuit is in the same direction. Therefore, you are going to get negative value there. So here you are going to get negative is 2.59 multiplied by 1 ohms. Okay, and then 20 ohms also you get negative, which is negative 20 multiplied by 2.59. Okay, there's no more resistor there, therefore you are going to get your answer is 25.61 volt. Okay, so the difference is below than like 5% or like 0.01. It's still acceptable. Okay, example, if you get like 24 and 25 volt, is going to be totally wrong. Okay, this one, the front part is same, therefore you can actually assume that the current I1, I2 and I3 that you get before is correct. Okay, so that's how you solve for you to find the potential difference. Okay, but the things that you need to understand here is make sure that when it comes to the terminal voltage and potential difference, always use direction that has been corrected, okay, before you start your calculation. Okay, so we have another questions for this one. Okay, so the question first, they ask you about to find the currents when the weak battery is connected to it. So it means that we are going to focus only at this part. Okay, so example, if you only connected to the weak battery, you can actually use the concept of Ohm's law for you to solve this, but you already learned about the Kirchhoff law, therefore you can actually use that kind of method too. Okay, so example, if I want to use Kirchhoff law here to solve this question, therefore I'm going to like put here one big loops. Okay, I'm going to put clockwise assumption loop over there. Okay, because you only connected to the weak battery, therefore the I2 here and the I3 here, the currents will be the same value. Okay, because in series. Okay, so here, okay, I2, okay, I2 equals to I3, therefore I'm going to put it as a only I. Okay, so I'm going to use the Kirchhoff law. Okay, so the 0.10 ohms there will be in the same direction. The assumption loop is in the same direction of the current of the I over there, so it's going to be negative, so negative 0.10 I. Okay, and the voltage 10.1, okay, the assumption loop is moving from lower to higher potential difference between the terminal. Okay, so I'm going to get positive 10.1. Okay, and for the RS here, okay, because my directions of assumption loop in the same direction with the current inside the circuit, therefore you are going to get negative 0.15 I. Okay, and is going to be equivalent to 0. Okay, so simplify this equation, therefore you are going to get here is I equals to 10.1 over 0.25. Okay, you are going to get your answer is 40.4 ampere. Okay, done with the question A. Now we are going to focus on question B. Okay, so for the question B, the good battery also connected, so means that we are going to look at the whole circuit. Okay, so we are going to look at the whole circuit here, and then definitely we need to find three equations, which is one equation come from the Kirchhoff currents law, which is you can choose at the junction A or at the junction B. So I'm use junction B to come up with the equation of the Kirchhoff currents law. And then because you have two free space here, therefore you are going to have two equations come from Kirchhoff voltage law. Okay, so let's start. Okay, so before we start using the Kirchhoff law, we need to find first the resistor value here and here. Okay, the resistor of the jumper. Okay, so we can actually refer to the table. The resistivity for this copper going to be 1.68 power of negative 8 ohm meter. Okay, so use the previous formula that we have learned, which is R equals to resistivity length over area. So you are going to get 1.68 power of negative 8. Length is going to be 3 meter. Okay, and the area going to be pi r square. So pi multiplied with the 0.50 centimeter here. Please convert that into centimeter. Please convert that into meter. So 5 power of negative 3 to square. Okay, so you are going to get this value of resistor here going to be 2.57 power of negative 3 ohm. Okay, so once you're done with that, then you can actually start using the Kirchhoff law. Okay, so I'm going to draw my assumption loop, which is going to be both clockwise motion. Okay, so I'm going to start with the first loop. Okay, so I'm going to start at 0.02 ohms. Okay, because the current I1 is in the same direction with my assumption loop. Therefore, the resistor R1 there, RJ here and RJ here are going to have a negative voltage. Okay, so negative 0.020 I1. And then for the potential difference here, okay, so I'm going to use the assumption loop, which is moving from lower to higher potential difference. Therefore, I'm going to get positive 12.5. Okay, and the RJ there also a negative because the current inside the circuit and the current for the assumption loop is in the same direction. Therefore, negative 2.57 power of negative 3 I. Sorry, this is going to be I1, and also negative 4.73 power of negative 3 I1 for this one. Okay, so done with the path of I1, then we are going to focus on the path of I2. Okay, because like I mentioned before, for the equations you need to consist of this one whole circle like this one. Okay, so this is going to contribute to the first equation. Okay, so the assumption loop here is moving from higher to lower potential difference. Therefore, I'm going to get negative 10.1. And then for the resistor here, because my assumption loop and the current inside the circuit in the opposite direction, therefore I'm going to get positive voltage. So here going to be 0.10. I2 equals to what? 0. Okay, please make sure that you double check with the sign first, okay, before you proceed with the next one. Okay, simplify everything for this one. So you are going to get here is, so I'm going to get 0.02514 of I1. Okay, and then plus with the 0.10 I2 equals to 12.5 minus 10.1 equals negative 2.4. Okay, so this is the first equation. So we are going to proceed with the next equation, which is focus on this part. Okay, so I'm using the assumption loop, which is clockwise motion. Okay, I'm going to start at 0.10 ohms first, which is this one. Okay, so here I'm going to get negative voltage because the second assumption loop same with the direction of the current inside the circuit. Therefore, I'm going to get 0.10 negative I2. Okay, and the potential difference of the battery here is the assumption loop is moving from lower to higher. Therefore, I'm going to get positive EMF. Right? Okay, so there's no more resistor or potential difference at the path I2. Therefore, I'm going to focus for the I3. Okay, so the I3, we have only one resistor here, and the directions of I3 is the same direction with the assumption loop number 2 here. Therefore, I'm going to get negative value. So negative 0.15 I3 equals to 0. Okay, so rearrange everything. So we are going to get negative 0.10 I2. Okay, I change. Okay, minus with a plus with a 0.15 I3 equals to 10.1. Okay, so for you to, before you put it inside the calculator, definitely you need to make sure that the unknown both same for first and second equation. Okay, so for the first equation you have I1 and I2 as an unknown, but the second equation you have I2 and I3 as an unknown. Okay, just change the one that difference. Okay, so now I2 is the same for both equation. Therefore, you can change either I1 or I3. Okay, but for you to change that, definitely you need to use Kirchhoff currents law. Okay, so for you to use the Kirchhoff currents law, I'm going to choose B as my junction there. Okay, B. Okay, so the I1 going to be into the junction, I2 also into the junction, means that both are going to be positive. Okay, but I3 going to leave in the junction, therefore it's going to be negative. So I'm going to get my equation is negative I1 minus positive I1 positive I2 minus I3 equals to 0. Okay, now I'm going to change my I3 here, so I'm going to put my I3 as subject, therefore I'm going to get I1 plus I2. This equation, I'm going to insert that into this formula. Okay, so I'm going to get that the new equation is going to be 0.10 I2 plus 0.15 I1 plus 0.15 I2 equals to 10.1. Okay, simplify everything, therefore I'm going to get my equation is 0.15 I1 plus 0.25 I2 equals to 10.1. Okay, so this one going to be my third equation. And okay, I forgot to put negative here. Okay, so I need to put negative here. Okay, therefore that's why you need to double check everything first. Okay, okay, once you're done with that, therefore we are going to put that inside our calculator. Okay, so the I1 that I get is going to be I1 is 75.6 ampere, and the I2 that I get is negative 4.98 ampere. Okay, so if you get negative here, therefore you need to give a statement, because the direction negative here means that the direction of the current inside the circuit here is wrong, therefore here is moving to the right, therefore for you to fix that, you need to give a statement, the directions of the current should be to the left. Okay, but for the positive one, you don't have to give a statement. Okay, so we already find I1 and I2, therefore we can actually find the I3 based on this equation here. Okay, so the I3 equals to I1 is 75.6 plus minus with the negative 4.98. Okay, make sure that you use the original directions first, because as you can see that from the starting we use the wrong direction, therefore for you to find the unknown current, you need to use the wrong direction first. Okay, so here you are going to get your answer is 75.6 minus with the 4.98, so you are going to get 70.62 ampere. Okay, so you are done with that. Okay, but the things that you need to understand here, it doesn't mean that the unknown can only be current. It can be EMF, where you need to find the EMF of the battery. Okay, so we can actually try that questions in a different video. Okay, we are going to discuss that in different video. Okay, so okay, this is the last one. Okay, so the question asks you to find what will be the current I even before the starter motor is engaged. Okay, and why will this cause the battery to explode? Okay, so first thing first, we are going to find the current. The RJ there, we already find that, which is RJ there is going to be 2.57 power of negative 3 ohms. Okay, so I'm going to like draw a big loop here. Okay, so 12.5 here are going to be negative because it's moving from higher to lower potential difference. Okay, and the 0.02 over there going to be positive because it's opposite with the directions of this current inside the circuit. So to make it easier, I'm going to do it like this. So it's going to be positive 0.020 plus with 2.57 power of negative 3. Okay, sorry, this one I forget to include. Okay, so plus with this 2.57 power of negative 3 I. Okay, okay, and then sorry, I forget to insert with the 0.10. Okay, plus with the 0.10. Okay, this is I, and then this one is going to be negative because it's moving from higher to lower potential difference, therefore negative 10.1 equals to 0. So you need to find I here. Okay, So you are going to get the value is, so here, wait, I'm going to put it 12.5 plus 10.1. So the combination of this one I get is 0 0.12514. So I'm going to get my answer is 180.6 ampere. Okay, so basically this is like a very large current. So why will this cause the battery to explode? Because if you put power equals to I square R, okay, so you are going to get, okay, yeah, I insert that first. Okay, I square is going to be I 180 square. The resistor here going to be 0 0.10. Okay, so you are going to get here is 3262 watt, which is basically high value. Okay, so what happens is when the current is flow inside the battery is going to cause this battery to be hot. So what happens when it's hot is going to be explode, because 10.1 volt is like very small voltage of the battery. So with this kind amount of power, definitely is going to be explode. Okay, so I think that's all for now. So we are going to discuss a different kind of questions involve Kirchhoff law in the next video. Okay, so hoping that you grab first the concept of Kirchhoff law, the concept of resistor in series and parallel, and the concept of EMF. Okay, so that's all for now. So thank you very much. Assalamualaikum and goodbye.